This is Europe, and some recent work has shown that, I don't know if you can see it or not, this outline right here represents the outline of the ice cap that was covering Europe, northern Europe, at the end of the last ice age. And I have never really shown you many maps of that, like I have North America. But I don't know if you can you see this faint line right here? Yeah. That represents the ice sheet. So it was completely burying Scandinavia and the Baltic Sea. There was no Baltic Sea. There was no North Sea, actually, at all. This, during the lowered sea level, this whole area, these were not islands, right? During the Ice Age, this was all one landmass. If you remember, I've explained that around 14 to 15,000 years ago, during the depths of the Ice Age was about 18,000 years ago, the age of Scorpio. Between 14 and 15,000, the climate of the Earth began to warm gradually, and the ice caps began to shrink. At that time, they began to shrink back, and they exposed the land between the British Isles and the European mainland. And the woolly mammoths followed them. This was one of the prime woolly mammoth grazing grounds at the end of the last ice age, what is now the bottom of the North Sea. Well, somewhere in there was a gigantic flood that came off of the European ice sheet. And it flowed right down here and essentially created what is now the English Channel. And some of those studies have shown, if you see where the closest part, let me get my pointer out. Right here, this closest part where the English Channel comes very close, this is where they always swim across right here. Okay, that is this area right here. And the whole English Channel is a giant scoured megaflood channel, similar to some of the Missoula flood, but even bigger than Grand Coulee, on the scale of some of the largest channel scabland complexes. And you can even see there are the pointed prow-shaped fluvial landforms, but they're all underwater. And these are from recent surveys. See, here's scabland type erosion in here. Channel floor megaflood landforms. So here you can see, like, notice the pointed prow. To anybody who's looked at the landforms of the Missoula flood will instantly see the similarity between this channel scabland complex and the and the English Channel. And if you were able to drain the water out of the English Channel, what you'd be looking at would be a channel scabland. Just very similar to what we see out in Washington State. The English Channel? How deep is the English Channel? I don't know, a couple hundred feet at least. Well, remember, the thing to remember is that during the Ice Age, when the ocean was 400 feet lower, the English Channel was not an ocean channel. It was, like I was saying, it was land.
Yeah, but it's only about 80, 90 feet deep.
So yeah, that would make sense. So it didn't drown until the sea level rose.
Right.
So what we have here is a big flood that flowed across the land before the sea level rose. So it was able to scour these canyons and create these fluvial landforms, and then the sea level rose and drowned this eroded landscape. But what this tells us is that the catastrophic melting wasn't confined to just North America. And that has to be taken into account when we start trying to create a realistic model of what exactly happened 12,000 years ago. If this, in fact, dates to 12,000 years ago, which they're still working on dating this, and the dates are pretty wild, ranging all over the place. Okay, well, let's get on, because I still want to get to the X factor. Okay, but something else I also have here for you is that, yes, then there's the giant floods in the Altai Mountains of Siberia, which until the recognition of these giant floods in Siberia, the Missoula floods were considered to be the largest floods ever documented in the whole history of the Earth, with peak discharges ranging from 100 million up to almost 1 billion cubic feet per second. Well, then with the thawing of the Cold War, American geologists discovered that Russian geologists had been over in Siberia studying the effects of a similar scale flood in Siberia. So what we're looking at here is the evidence starts coming in. You know, we're looking at North America, we're looking at Northern Europe, we're looking at now Siberia. So clearly something was able to cause melting, you know, completely in the Northern Hemisphere. Of course, there weren't as big of glaciers in Siberia, we don't think, as there were in North America. So where did those floods come from? So,
More energy.
so now, yes, now we need more energy. Did you hear what Paul said? Paul just, really, he's nailing it. Because as the magnitude of the effects increase, yes, we need more energy. More energy. I mean, we're talking now about some pretty extraordinary amounts of energy coming from somewhere.
So they occurred at the same times at night.
Well, see, that is the controversy, and as the dating gets better and better, it does appear that the Siberian flooding was at the very end of the Pleistocene, which would mean it was happening at or very close to the same time as the North American flooding. And here you can see some of the effects, the giant current ripples that should be familiar to you because you've seen pictures of the things that I've taken out west. Let's see.
You have not done this lecture.
Yeah, maybe not. Okay, these are some of the giant current ripples in Siberia, and you can see they're very similar and on the very same scale as the giant current ripples out in Washington State.
So would that have meant that, like a meteor or something, occurred at the top of the earth to make the floods come down?
Well, actually, this flood is flowing north.
Really?
Yes, it's flowing towards the Arctic Sea.
Huh.
Yes. Huh. Yeah. And here are some of the valleys that it flowed through. And if from your slides that I've shown you of the Clark Fork Valley, where I've shown you the bare rock up the sides of it, and then you can see where the soil actually starts with trees and plants growing on it, because that's above the water line. Below the water line, it's just bare rock. Now look on here. Can you see the water line on the cliff side?
Yep.
Right up there. And then you look at the bottom and you see the other, characteristic feature is these giant sediments that filled the valley floor and have now, I don't know what river this is, maybe it's the Altai River, just like the Columbia has cut down into these massive sediments on the floor of the Columbia Channel. This is now cut down into these massive flood deposits on the floor of this canyon. And here we have, this is also familiar to anybody who's seen the Bonneville flood or Missoula flood stuff. Brad, you've certainly seen stuff like that on our trips. Bouldery, hummocky, chaotic mounds of stuff that's just dumped. Probably because what you've got is this huge gush of water loaded with this stuff, and then also in that water you've got massive icebergs. And then when the rush of water finally begins to decline, the icebergs come to ground, the icebergs melt, and they leave the hummocky mounds. So you've got a really chaotic event here. And here you see terracing. See the flat shelf? That flat shelf was built by this huge flow of water coming through here that probably was up above this, flowed through this valley, and when the flood finally started to decline, it built this flat layer across the bottom of the valley. And then the modern river that began 10,000 or 12,000 years ago has cut this channel right here. Just exactly like we see, along the Snake River or the Columbia River out west. And here you see the terrace forms with the channel. So when you start beginning to see, if you ever travel out west now and you begin to see stuff like this, hopefully you look at it with the eye of recognition and understanding, and not just like the average person driving by it and glancing at it and never giving it a second thought. Notice here, here's your terracing, flat area up here. At one point, this would have been continuous across here. Then the residual waning floods create this channel right here. So, actually in here, That's a whole current ripple field out there. And it's all of these things taken together that prove the case. And here's some of the kind of sedimentary deposits left by the Altai floods. And certainly you're going to see the similarity, I think, between that and some of the Missoula stuff. Now, if you look at there, let's go to, see, here's the kind of stuff I'm talking about that we can compare to the Altai floods. And you've seen this. This is the kind of stuff you learn to look at and actually look for if you're, if you're a catastrophist. If you're out there actually looking for the real world evidence for past catastrophes, this is the kind of stuff you want to learn to recognize. And look at what?
I was just looking at the scale of it with the person in there.
Well, yeah, you can see that the whole hill here is basically a giant flood deposit. And these things are all over. And this is one of my points that I'm trying to drive home is that, to the average person, let's say the average, person up here hiking, hunting, camping over this landscape, they'll be walking over these hills without ever having a second thought as to what's under their feet or what story is being told under their feet. But then if you come across a gravel quarry like this, there it is exposed right there for you to see. And all over the southern Appalachians, it's all there. You can see where the whole southern Appalachian mountain chain underwent extraordinary erosion at the end of the last ice age with gigantic landslides all over. But the problem in the southern Appalachians, of course, is with 30 to 50 inches of rainfall per year in heavy forests, people can go up there without ever really seeing. But when you hike along the creek hollows and you go up, that's when you can begin to see boulders the size of this room that have been washed down from the flanks of the mountains. And you got to say then, how in the world do you get a boulder the size of this room, 2 miles or 3 miles from its source up on the side of the mountain down to the bottom of the mountain in the creek hollow? And it's not by itself, it's...
You know that in the Alps, you have the same thing. I've done a lot of hiking there, and I always wondered about what I saw, and I've only learned now, through watching your stuff, what it really meant. But
right.
A lot of that there.
And then, the other thing you need to learn how to do is differentiate between a water transported rock and an ice transported rock. And they're very different. And once you learn to see that, you can look at it and go, because some of what you were looking at may have been ice. But see, there again, I haven't studied the Alps to know whether there's evidence of catastrophic melting over the Alps. There certainly was huge amounts of ice over the Alps. I mean, the Matterhorn is all created by being surrounded and almost completely drowned in ice. Now, out west, we have this interior basin. Now, I don't know if you get the orientation or not, but this is Great Salt Lake, and this is what's called the basin and range. Here's basins. You notice there are basins, and they're separated by mountain ranges. And if you look at all the basins, they have these flat floors. And why is that? Because at the end of the last ice age, they all held huge lakes. And all of this here, the basin and range province, does not have an outlet to the ocean. In other words, it's a basin. It's anything that runs into, like here's Death Valley. Anything that runs into Death Valley, like if the water here flowing, it'll flow into the lowest part and then it'll sit there. Well, at the end of the last ice age, and here again dating is controversial, and no attempt has been done to effect a wide-scale correlation of dates. But if you take all of the dates, if you take all of the evidence for bodies of water in the Basin and Range province at the end of the last ice age, it would have looked like this. Huge amounts of water. Absolutely huge amounts of water. And no outlet to the sea. That's important. See, up here, up in Washington, you had an outlet to the ocean. So if there was a glacial Lake Missoula, it was able to flow right on out the Columbia River and out to the ocean. This has no river connection with the ocean, so any water pouring into this as the result of rainfall or runoff collects like, you know, water in a pond after a rainstorm, and then it dries up. And essentially, the first 4,000 or 5,000 years of the Holocene was this water evaporating away.
That area on the corner, that big blue area?
That's the big valley.
San Joaquin, I think.
Yeah, San Joaquin. I think it's the San Joaquin Valley. It's a big agricultural valley with a lot of fertile soil. But you see, the thing is there, it gets a lot of rainfall because of the mountains producing the rain shadow. And then this is all arid desert. However, here's the interesting part. During the last ice age, this area was also a very temperate area with grasslands and forests and huge herds of animals living. It was not desert. And then the end of the ice age came and it was drowned. And then over the next 3,000, 4,000, 5,000 years, all of this water evaporated away. And
that map doesn't show it really, but the outlet for that lake would be right out through like San Francisco Bay and into the Pacific right there.
oh, this lake.
Correct.
Yes. This one might have had an outlet to the ocean. But in this area, it did not.
Right.
In fact, if you follow right way down here at the bottom, all the way around, none of this area had an outlet to the ocean.
Where would the Grand Canyon be on that?
The Grand Canyon doesn't... Oh, yeah, this is it right here. Can you see it?
Yeah.
But yeah, it's Grand Canyon is right at the bottom down here. This is it right here.
So is it not the lowest area around?
What, the Grand Canyon? No, it's not. Because Grand Canyon, the rim of Grand Canyon is, yeah, it's right at, isn't the bottom of Grand Canyon just a little above sea level? I know that the northern rim of Grand Canyon is 7,000 feet above sea level. The canyon itself is about 5,000 feet deep. So that still puts it a good 1,000 feet above sea level. Whereas Death Valley, for example, which is this right here, is as much as
290 feet below.
almost 300 feet below sea level.
Randall, don't you think that water comes through the instead of evaporation, gone to the down part of the layer, creating water under the ground?
Oh, you mean groundwater?
Yeah.
In this case, not probably. Yeah, I mean, one thing we can say is that we certainly know that the groundwater in the Midwest was that whole aquifer. That what's it called? The big aquifer, the Oglala, is it? The big aquifer under the Midwest that was replenished at the end of the last ice age.
In Mexico, they have such a water.
Yeah, it's probable that it was. But bear in mind, throughout the ice age, there was lots more rainfall out here in these desert regions than there is now. So undoubtedly, there would have been a much more charged water table during the ice age than now.
Hold on to your pointer for a second. I know we're interrupting you a lot, but yeah, can I point something out?
Sure.
Just as I'm looking at this thing.
Tell me up, down, or you want to do it? Okay.
I don't know. See if you guys see this here.
What's Brad looking at? Oh, a circle. I see it. Yeah, here's what Brad's seeing.
Is that discernible there?
Yeah, I see it.
So,
All right. I think that's, yeah, Brad's discovered a new crater. And we'll have to enter it into the books. Bradley Crater. Notice, if you will, the one outlet. I said that this has no outlet to the sea, but there's one exception. And that exception is right up here. There's an outlet through the northern section of this. When this lake rose up over the area of Salt Lake, the water right here was almost 1,000 feet deep. And as you go north up this valley, these are the Wasatch Mountains right here. If you can see those right here, Now you'll see that the Wasatch, notice where the lake comes, the lake was lapping against the base of the Wasatch Mountains right here. And so when you fly over the Wasatch Mountains and you know what to look for, you can see right where the lake water lapped. See it? Now again, that's the kind of thing that, you know, I'm up in the airplane, craning my head out the window to see this stuff, and nobody else has the slightest clue what's out the window that they can look down and see. But there it is. You can see the shoreline very clearly.
How does that water get to the ocean? Going north?
Well, there was an outlet to the north. And when the water rose up to 1,000 feet deep, it was actually more like 960 or something, to this depth here, at the northern rim, there was a valley that was filled with sediment, and the top of that sediment was just about the same level as the high water level when the lake was at its maximum depth. It was just high enough that that was the lowest divide in the whole area, that whole gigantic basin that we looked at. The lowest area was that called Red Rock Pass. And the water rose up just enough to start to spill over that pass, and only that pass. And as soon as it did that, it started cutting the sedimentary layer down, which was 300 feet thick of softer sedimentary rock. And then it got to a sill of hard, I think it was granite. So the water rose up 900 feet, spilled over the divide, ate the divide and eroded it down 300 feet, and then the lake level stabilized at that level, and the Bonneville flood at that moment stopped. Now the lake level stabilized at that level, and then what you had was over the next 3,000, 4,000 years, that body of water slowly evaporated away. Going behind now, here's what you see. This was cut at the high water level, when the water rose up and spilled over the divide to the north. It then ate its way 300 and some feet down through the sedimentary layer, and then it stabilized at this level right here. So you see, now that you know what it is, you can see two distinct shorelines. The uppermost shoreline was the high water mark, represented by the magenta line. It dropped down 300 and some feet and then stabilized at that bed.
That they couldn't eat through. Where's the granite?
It's at this green line right here. So you can actually trace this shoreline around the basin, and then it comes right up to the channel at the north end, and it's at the same height as the hard granite sill. This is actually the shoreline of the lake, of Lake Bonneville.
So that was freshwater lake?
That was fresh water, right.
So then,
Okay, let me back up. It wasn't really completely fresh because you've heard of the Bonneville salt flats and the Great Salt Lake. There was a lot of minerals in that water, and it's those minerals that as the water evaporated down, the ratio of water to sediment diminished, so that as the water evaporated away, the water got thicker and thicker, filled with salts and sediments. And now if you look on the floor of Death Valley as an example, it's white because of the salts, just like the Bonneville salt flats. It's very salty.
The surface of the salt is smooth, and if it was mud, it would be all cracked and open.
Probably so, yes. Now as you go into the pass, what you'll find is that there are rock outcrops protruding that are this reddish rock is the softer sedimentary rock, and that's a remnant of what was originally washed away. So, as it said here, the red rocks, which gave their name to the overflow spillway of Lake Bonneville.
where did all the salt come from? That
Well, you know, the theory right now is that it, you know, it was stuff that was in the rocks that were, you know, when all of this water is collecting, it had to have been rainfall. Assuming it was rainfall, on all the surrounding mountains, we presume there's rainfall, and it's eroding these rocks, and the minerals in the rocks are going down as suspended sediment in the water that then accumulates in the lake water. Then as the lake water evaporates, the sediments, the suspended sediments, are left behind. Does that make sense?
Yeah, but the thing is why would there be a concentration of salt there when you don't see that? I don't know of other places on Earth. There might be. But.
Well, first of all, there's the unique topography here. The second thing is that a lot of the rocks do have those kind of minerals in them, in the surrounding mountains. Now, the only other possibility would be an ocean tsunami that could reach that far inland. But that's questionable. You've got an ocean tsunami that would have to cross the Sierra Nevadas, and I think it's much more likely to be rainfall. But a lot of rainfall. And this is looking through, see what you're looking at here is essentially what is now was a temporary river 300 feet deep flowing from left to right. And here you can see, have you seen this yet? This slide? Oh, okay. The water came from this direction, formed a right angle and flowed out this way. This was the channel that was cut by those waters spilling over the pass on the north end. And then at the mouth of that, there was a fan created, and Pocatello, Idaho is built on that fan. And you can actually see here's a channel that was cut where there was more of a concentrated flow coming out of here. And then that flowed into the Snake River. And if you look at this, the kind of stuff that it was carrying, like when I said when it washed through the pass, it plucked all of these huge boulders and then washed them north into the Snake River Plain. If you look at these rocks here, that's the kind of stuff that it was transporting. And you can see for scale there's a person standing right here. And then there's an outflow channel. You learn to recognize this was an overflow spillway where the water rose up to the rim and spilled over and cut that channel. And here's an example of, see, you can look at things like this, and when you can find the largest rocks that were carried by the stream, you can measure those rocks, and then that will give you a measure of the stream power that was involved. And these two were dropped down like a couple of twins, but this is an example of some of the sediment load that was being carried in the Bonneville flood. The Bonneville flood is considered to be the second largest, most energetic flood ever documented in the history of North America, second only to the Missoula flood. But the difference is that this was not fed by glacial melting. This is being fed by these overflowing lakes that, are in Utah and Nevada. And this is the canyon that it created. The present-day Snake River flows in that canyon. And this is Shoshone Falls. And there's another picture of the ship. Now what you can see here is a landscape that has been just completely demolished by gigantic energetic current flows. And we see the remnant of a major cataract right here. See, in other words, during the Bonneville flood, this entire scene was underwater. There was nothing in here that was exposed. So you had this whole canyon was basically filled. You can get a sense of the scale of it by looking at this bridge here. This is about 500 feet deep right here. That's actually a golf course right there.
That where Evel Knievel jumped the river?
It's near there. This is actually very close to where Evel Knievel did his famous jump.
Really?
Yep.
What bridge is that?
I think that's called the Hansen. Was that the Hansen Bridge?
This is Brian there.
Oh, Perrine Bridge. Okay. I think that's what it is. Okay, now take a look at this picture. This picture is a very instructive picture because what you see here is the modern mini river, Snake River, which is, probably 300 feet across, flowing in the channel of the ancient Bonneville flood river. Look at the size of the ancient river that was flowing there, that's no longer flowing. Now that, when you know and understand what that is, that's a pretty impressive piece of evidence right there. Here's a sedimentary deposit Can you see the humans, me and Brad out there? Yeah, that's a pretty amazing deposit right there. And I want to take people out so you can actually see and experience these things for yourself. You can't really get the reality of it by looking at pictures or slides. You have to go to these places in person with the knowledge to understand what you're not just standing in just this big rubble field that just got there, by some vague way. You're standing in the aftermath of a catastrophe.
Velocity of water.
Right. That's something I would very much like to do.
All right.
So there you can see these aren't ordinary river rocks, but they're rounded and eroded just like river rocks, like you were commenting, Linda. Now see, when you look at a rock like this is water erosion, not glacial erosion. Glacial erosion doesn't do this rounding like this. This is where it's rolling and tumbling into water. Remember I showed you the rubble pile over near in Siberia? And I called your attention, I said, notice this rubble pile? This is a rubble pile left in the wake of the Bonneville flood.
Oh, those rocks?
Yes.
Stuff like that on Mars too.
Oh yeah, there's stuff like that on Mars. See, and that's the interesting thing is you can begin to, start looking at other worlds. And now this is interesting because you see all of this debris piled up against this cliff. This is not normal talus that fell off the cliff. You see, notice that the cliff face isn't receded. The cliff is vertical. You see, if this talus came off the cliff would be at a receding angle. The cliff is vertical. This is stuff that was left after the floodwaters declined. So you could actually come in with a giant broom or a bulldozer and clean all that away and have a straight canyon wall all the way down to the floor of the canyon. You see that, Charles? That's rubble washed up against the wall by the receding flood currents.
There's a novel that's been written called Angle of Repose.
Yes.
It's well written. It's beautiful.
There it is. That's, Angle of Repose. That's exactly what that is. Oh yeah, you can see the human figure out in the midst, being lost in this gigantic boulder bar. And that's just a gigantic, much larger version of something you could see going down here to the, along the Chattahoochee River. And then this is actually one of the most important and interesting outcrops. We're looking at the Snake River flowing north, coming right up here. And there's a bar right here called Tammany Bar. It's this thing right here. And right all in here is a big gravel quarrying operation. You would be interested in this, Charles. Gravel pit right there. Now, notice what it says, Snake River, Tammany Bar, where the Missoula flood met the Bonneville flood. Lewiston, Idaho is on the left. Clarkston, Washington is on the right. And here's the river. Snake River flows up like this, comes out of Hell's Canyon, which would be right down here, forming the border of Idaho and Oregon. Flows up, hooks to the west, and flows out to the Columbia. But right here is the bar we just saw a picture of, and here's what happened. The Bonneville flood came rushing down the Snake River. The Missoula flood back-flooded up the Snake. So here's the Snake Valley with the gradient. Here comes the Bonneville flood going down to the ocean. Here comes the Missoula back flood, and the two floods met. And you can see it exposed right in this gravel pit. Now here's looking from an opposite hill, looking down into the valley, and right down here is Tammany Bar. Here comes the creek that it gets its name from, Tammany Creek, and the gravel quarry is right in here. Let's see if we can see that. Now we'll zoom in a little closer and take a closer look so you can see, yes, right there. Now look at this. Now this has got to be one of the most interesting outcrops I've ever seen in my life. You'll notice that there's two distinct types of sediment there, right? You don't have to be a geologist to go and say, look, that's two very distinct types of sediment. And you'll notice that the lower layer is much coarser than the upper layer, right? Well, remember what I was just talking about. The lower layer is gravel washed north out of Utah and southern Idaho. The silts on top are backfloods coming out of Montana, Washington, and Canada. And they meet right here. And what you see is the Bonneville flood gushing down the Snake, and then a Missoula backflood coming up with the waters losing energy, stilling out, and depositing their layer of fine silt right directly on top of the Bonneville gravels, with no evidence of any hiatus between the two events. And yet this outcrop has only been acknowledged a couple of times in the literature and never studied. And yet here, and to you geomorphologists now, look at the bedding. Which way was this water flowing? Left to right or right to left? From right to left. Look at your tilt. It always tilts down in the direction that it flows. And you can see the tilting here. There were huge currents just gushing, loaded with this gravelly stuff, coming up. And then right up here, you see the Missoula backfloods. Now, if you try to understand the difference between the two. One is high energy moving down the slope, but the other one is a backflood moving up the slope. So you can see the signature of the two levels of energy right here in this deposit. And there you can see a cross-section of the whole impressive feature. And here is gravels taken out from Utah and southern Idaho, and here are silts that were carried from as far away as Canada, British Columbia. And they meet right here. And almost no geologists that I've read, or any of the ones that I've talked to out there or gone on field trips with, have understood and grasped the significance of that evidence right there, telling us that these two flood events happened simultaneously. And here, let's see. Here you can look at, here's some of the Missoula backfloods. Now this is stuff that's come 200, 300, 400 miles, 500 miles. And this is where the currents are coming to the end of their journey as they're slowing down, and then they're going to stop, and then they're going to reverse, and then they're going to flow west out to the Pacific Ocean. But where they come in and they stop and do that reversal, that's where they create these really interesting, this architecture, and that's what this is. We're looking at this flow architecture here. And a sedimentologist can actually read that flow architecture and see what those currents were doing. And I'm still learning that, but there's enough that I can now see that you have, what you have indicated here is currents that are reversing direction. You see, we're right here at the limit of the Missoula backflood. You've got the main channels, and this big gush is coming down out of Canada, right? And then you've got these tributary valleys, and as the main valleys is overwhelmed with water, water begins backing up the tributaries. The Snake River was tributary to the Columbia and the Channel Scablands. So when this huge tsunami of water overwhelmed the Channel Scablands and the Columbia, a tidal bore, if you will, began to move 100 miles up the Snake River, all the way to Lewiston. And that was where it stopped. And then it turned around and flowed back out. But where it stopped, this is what it built. So if you go there, you can actually look at this and begin to read the whole story unfolding.